Hello, I'm Ryan with High Desert Math Tutor, and today I want to talk to you about calculus. So calculus has two main sides. Now, in the first calculus class, you typically are first introduced to what is called differential calculus. You later move on to what's called integral calculus, where in Calc 2, you'll spend most of your time focusing on integral calculus. And when you go into Calc 3, you basically repeat Calc 1 and Calc 2, but everything is at a higher dimension, so 3 dimensions or more typically. We'll get into the details more in a moment, but to begin, the first major half of calculus is called differential calculus. And differential calculus refers to what are called derivatives. Now, a derivative is nothing more than a rate of change. So derivatives are a rate of change. Now, for those of you that are thinking to yourselves, rate of change, that sounds familiar. What are rates of change? So a rate of change, in one word, is known as a slope. So in reality, a derivative, or the first half of calculus, deals with nothing more than slopes. But we look at slopes in a slightly different light than you had in algebra, trigonometry, pre-calculus. But we'll get into that more in just a moment. Now, jumping over to the other side of calculus, which is integral calculus. Integral calculus is referring to what we call integrals. And an integral, more or less, is nothing more than the area between a given curve. So it's a function you would be given, and the x-axis. Basically, that is what an integral is, which we will dive deeper into that in just a moment. So looking at differential calculus more deeply for just a moment, if we are familiar with slope from algebra, then why would we talk about slope again in calculus? Well, it turns out when you were studying slope in algebra, pre-calculus, the slope you were referring to is something called average slope. So average means more or less the middle. And if we just draw ourselves a curve for just a moment, so we'll draw some coordinate axes. X-axis, y-axis. Let's say we have a curve that looks something like this. So the curve goes up, then down, then up again. Well, if you recall, many of the slope questions you would have dealt with previously told you a starting point and an ending point that you wanted to find the slope in between. So I could say I want the slope from here to here. And what you would have done previously is found the straight line that brings you from point A to point B. Now that is average slope, but if you notice, there's something more going on here. This slope from this one point to the other point, it does not look anything like this curve. And if we were to kind of experiment with this, let's say that we slide this lower point up a little bit. We move it right here, and we connect these right here, these points. Well, let's say we move the point up a little further. Right here, we connect these points. So we get something like that. We move up a little further. where we're almost touching the same point, if you notice, our slope starts to look a little bit more like it's touching the outside of this line right at that point. So average slope has 2 points. It tells you the exact slope you need to get from the first point to the second point. But calculus focuses on something called instantaneous slope. And instantaneous, where have you heard instantaneous? Think back, like, come here right this instant. That means come here right now, or over a very small period of time. So in calculus, we like to think about slope, more or less at a single point. So for calculus, let's say we look at a point right here. Instead of saying I want the slope between this point and this point, you could say, just give me the slope at exactly this point. I want to know how steep this curve is at that exact point. And calculus can help you find a slope that touches perfectly that point, which gives you the slope in that instant. So differential calculus focuses on slopes, rate of change, but the slope we're focusing on is instantaneous slope, which is very useful in our day-to-day lives. As you'll see, there are many uses for slope and many special characteristics of maximizing your income or minimizing how much time you spend working on a project, or minimize how much money you spend manufacturing some sort of good. A lot of those sorts of problems, those questions you might have as how to do that, you can solve questions like that very easily using instantaneous slope, also known as a derivative. Now, jumping over to integrals for just a moment. As we've said, an integral, in a very basic sense, is just the area between some curve, like this blue curve, and the x-axis. So if we think for a moment, what area formulas may you be familiar with from algebra, from trigonometry? Well, most of us can probably agree we've seen area formulas for, say, a circle. We've seen area formulas for rectangles, which, by the way, a square is a rectangle. And we've seen area formulas for triangles. But in our day-to-day lives, how often do we see perfect circles, perfect rectangles, perfect triangles? There are many instances where we actually are interested in something that's not that perfect. And this is where integrals can come in handy. So if we draw another set of coordinate axes over here, this time we'll look at a similar curve, essentially the same curve as before, but we'll think about a different characteristic. So say that I'm looking at this curve and I ask you, what is the area from this point or that region to this region? So I want to know how much space is underneath the curve from this x value to this x value. That's not a perfect rectangle, it's not a perfect triangle, and it's not a perfect circle. But using techniques from integral calculus, we can find the exact area underneath this curve. Now, as I mentioned here, there are many problems, real-world problems and situations that are not simply asking for slope, but we can use slope to answer many questions. Well, here, there are many engineering problems, many economics problems, and just any problem really you can think of with money, space, energy, that can actually be answered by looking at areas under curves. So integral calculus helps us with irregular areas, which extends to many problems beyond just how much space is under the curve. But one last major connection I want to show you between differential calculus and integral calculus is that a derivative and an integral have something very special connecting them. But before we discuss that, let's just take a step back. Think about addition and subtraction. What's the connection between addition and subtraction? Well, subtraction is the opposite of addition. But then what about, say, multiplication and division? Well, multiplication is the opposite of division. Just like, in a basic sense, many roots are the opposite of many exponents. Well, here, it turns out derivatives are the opposite of integrals. So we can just say that a derivative is the opposite of an integral. And that means an integral is the opposite of a derivative. Which means if you have some sort of formula that you've taken the integral of and you want to undo that, how would you undo that? The opposite of integration would be differentiation, taking a derivative. But say you have a function that you've taken the derivative of and you say, well, I'm ready to undo that. Well, you can undo a derivative by taking an integral. So there's a nice connection between differential calculus and integral calculus that is very useful, obviously in calculus, but then it's very useful when you're looking at physics problems and many real-world physical situations that you're trying to answer questions. But the last thing I want to just make very clear to you, because many people begin calculus by studying something called limits. And when they study limits, they kind of ask themselves, like, why did we ever talk about that? I see that we talked about limits, we move on to derivatives, and then eventually we get to integrals, but people don't understand fully, why do we care about limits? Now, I've made other videos about limits and conceptually what they actually mean, but I want to show you the definition of a derivative is this, the mathematical definition. A derivative is a limit as h goes to 0 of f of x plus h minus f of x over h. The definition of an integral is the limit as n goes to infinity of the sum from, let's say, I equals 1 to n of f of x sub I times the change in x. So I don't want to get into the details of what this formula means. I don't want to get into the details of what this formula means in this video. There will be other videos for that, but I want to point out to you that a derivative is a limit and an integral is a limit. So, and let me actually make one quick change to this formula, slightly nicer. So if I just write this integral x dx, that's slightly better. So an integral is a limit. Now, both sides of calculus are built on limits. So the things that you study in the beginning of calculus, which are limits, are extremely important because both a derivative is a limit and an integral is a limit. And when you're studying the properties of limits, that means indirectly you're studying tons of the properties that support differential calculus and integral calculus. In other words, when you're studying limits, adding limits, subtracting limits, dividing limits, multiplying limits, that applies to derivatives and that applies to integrals. So I hope that was a helpful just kind of introduction to the background of what calculus is, focusing on slopes and areas. And I hope it kind of gives you an idea of the road ahead, where Calc 1, you'll see both of these. Calc 2, you'll mainly dive deeper into integration. And then Calc 3, you'll spend most of your time relearning all of this, but in higher level dimensions.